Welcome everyone to the videos of Chapter 17 of the Crystal Clear Electronics 2 curriculum. In this chapter, you'll get an insight into the theoretical background of electric motors, learn about the types of motors, and then we'll talk more about their control. In the fourth video, we will build a simple circuit with a DC motor, so we will need PWM generation with a microcontroller and an H-bridge circuit. But we won't stop there, we'll measure the motor speed with a Hall effect rotary encoder, adding an element of excitement to our learning journey. The presenter of today's chapter is Szabolcs Vereb, who currently works as an assistant lecturer at the Budapest University of Technology.
Welcome everyone. In the videos, I'll be assisted by Rebecca Duke, an automotive engineering student at Széchenyi University, who is also part of the university's engine development team called Sengin. You can see some different devices here, which we will demonstrate in the upcoming videos. But, as a preview, here you can see the asynchronous motor of a kitchen hood. This is the motor of a drone, and here on the table there are also all kinds of switching devices such as MOSFET bridges and IGBT bridges. Well, you can probably tell from their sizes that these are high voltage and high current devices. The reason for that, as well, we're not going to be dealing with any kind of converter connected to the mains, but at the same time, I'm a power electronics engineer, so I've got these kind of components in my drawer.
If you're interested in electric motors, stay tuned for the videos of Chapter 17. And now let's sit at the table and take a look into how these devices work.
By the beginning of the 21st century, electric motors had become part of our everyday lives. We use them when we turn on the washing machine or start the extractor fan. Other examples are when we go out into the garden to mow the lawn or trim the hedge, or when we want to do some DIY. Almost all household appliances, telephones, and computers have electric motors, and nowadays, office work would be unthinkable without electric motors. They are also playing an increasing role in public transport and personal transport, for example, power steering motors, electric window lifters, wipers, motorized seats, mirror adjustment, just to mention a few. But let's not forget electric scooters or e-bikes. Nowadays, they've become indispensable tools in almost any manufacturing process. In addition, electric machines are one of the reasons why clean water flows from the tap, and they play an indispensable role in energy production as well. With these few examples, I wanted to illustrate that in our lives, if we want to find areas free of these devices, we have to search with a magnifying glass.
In this chapter of the curriculum, we will first learn about the basic physics of electric motors, why they are popular, and the different types. Then we will dive into the control of these motors, and finally we will bring the electric motor in the development kit to life through an experiment.
The 1800s were the years of electricity in physics. Among other things, the world's mathematicians and physicists were working to understand the phenomenon of electricity, the forces and interactions involved. In 1820, Hans Christian Ørsted discovered that a magnetic field interacts with a conductor carrying current. A year later, Michael Faraday demonstrated by an experiment that a circular electromagnetic field is generated around a current-carrying conductor.
The first real motor was created by Ányos Jedlik in 1827, creating the ancestor of the DC motor. Although his motor, or as he called it, the lightning magnetic self-rotor, was only an experimental example, it was identical in construction to the DC machines used today. It included a stationary and a rotating coil, as well as a commutator, which will be discussed in more detail shortly. The motor in the picture is on display at the Hungarian Museum of Applied Arts.
An important milestone in the dawn of the electric machine was the patenting of the dynamo principle by Ernst Werner von Siemens in 1867. Although the patent was issued by Siemens, the dynamo principle, also known as the principle of self-excitation, was also recognized by Ányos Jedlik in the late 1850s. We will explain this principle later for ease of understanding.
As these early experiments show, rotary motion in electric motors requires the interaction of magnetic fields. For all types of motors, the rotation can be traced back to a rotating magnetic field, which is effectively a variable magnetic field created by a rotating, permanent or electromagnet. To better understand how motors work, we need to delve into the mysteries of electromagnetic fields.
It's important to state a fact that is easily verified by experiments and natural observations. A constant, non-varying magnetic field does not interact with a constant, non-varying electric field. However, it does exert a force on moving charges, called the Lorentz force, the magnitude of which can be calculated by multiplying the magnitude of the charge by the magnitude of the component of the charge's velocity vector that is perpendicular to the magnetic field and the magnitude of the magnetic induction vector. The vector of the awakening force is perpendicular to both the magnetic induction and the direction of the perpendicular velocity component Vm. This is easily illustrated by the right-hand rule from physics class. With the index finger pointing in the direction of the velocity vector of the moving charge, and the middle finger pointing in the direction of the magnetic induction vector, the thumb shows the direction of the Lorentz force. Let's perform the following theoretical experiment. In a constant magnetic field, place a pair of conducting rods parallel to each other and move a third conducting rod over them. The Lorentz force acting on the positive charges is marked in the figure. Of course, the negative charges are also subject to a Lorentz force of the same magnitude, but in the opposite direction. During the experiment, the Lorentz force causes the positive charges to migrate to conductor 1 and the negative charges to conductor 2, creating a voltage difference between the two conductors.
It's important to note that positive nuclei in metals cannot move. Only the negatively charged electrons can move in the conduction band.
This is true. However, the charge separation will still occur. Conductor 1 will be more positive and conductor 2 will be more negative. The separation of charges in a conductor moving in a magnetic field due to the Lorentz force is called motional induction. The voltage induced by this phenomenon can be calculated by multiplying the distance between the two parallel conductors, the component of the velocity vector of the motion perpendicular to the magnetic field, and the magnitude of the magnetic induction. This phenomenon also works in reverse, meaning if a voltage is applied to conductors 1 and 2, and a conducting rod is placed on them, the rod will move. The voltage will cause a current to flow through the rod, which is nothing more than a flow of electrons, and the moving charges will interact with the magnetic field. We can determine the direction of the awakening Lorentz force by the right-hand rule. Now, the direction of the charge's motion is the same as the direction of the current, and the magnetic induction vector is pointing upwards, so the force will move the rod towards the left side of the figure, which results in the rod's velocity vector being in that direction. There are two other types of electromagnetic induction: resting induction and self-induction. In resting induction, both the direction of the magnetic field and the position of the conductor are unchanged. In this case, a change in the magnitude of the magnetic field induces a voltage between the two ends of a conductor looped in a circle. The polarity of the induced voltage is determined by the left-hand rule. If the thumb of your left hand is pointing in the direction of the magnetic induction vector, the end of the wire towards which your bent fingers are pointing will be more positive. The magnitude of the induced voltage can be calculated by multiplying the change in the value of the magnetic induction and the perpendicular projection of the looped conductor in a plane perpendicular to the magnetic field. Then the result is divided by the time elapsed during the change.
Transformers work on the principle of resting induction. A lightning strike can be a very extreme example. The powerful lightning current changes in time, creating a swirling magnetic field around itself and inducing voltage in nearby conducting loops. This can even destroy electrical equipment.
Self-induction is virtually identical to resting induction in physical terms. We distinguish between them because in the case of self-induction, the changing magnetic field is not the result of some external process. A typical example of self-induction is a current-carrying conducting loop in which you suddenly want to interrupt the current. the current initially flowing has created a magnetic field around the conducting loop. When the current is terminated, the decreasing current results in a decreasing magnetic induction, which induces a voltage, as described in the phenomenon of rest induction. In many cases, this phenomenon causes an unpleasant overvoltage, for example when trying to turn off a relay's coil with a semiconductor. As you may have learned in the crystal clear electronics curriculum, it's a good idea to connect the diode in parallel with the coil so that the self-induction voltage generated when the relay is switched off is limited to the diode's forward voltage.
The dynamo principle, also known as the principle of self-excitation, exploits these physical phenomena. You may have noticed that bodies made of iron are themselves magnetized in a magnetic field. As soon as the external magnetic field is removed, the magnetism of the iron body does not disappear, it only weakens considerably. This is called remanent or residual magnetism.
Imagine making a coil around such an iron core. In the weak magnetic field, moving a conductor perpendicular to the field lines induces a voltage between its ends. If this voltage is applied to the coil, a current will flow through it. The current causes the coil to create a magnetic field, which either adds to or weakens the remanent field of the iron core. It depends on the polarity of the voltage applied to the coil. Suppose we have connected it with a polarity that causes the current flowing through the coil to strengthen the remanent magnetic field of the iron core. A positive feedback loop is then created because the higher the current flowing, the stronger the magnetic field, and the stronger the magnetic field, the higher the voltage induced in the conductor, therefore the higher the current. This means that it will be increasingly more difficult to move the conductor in the magnetic field, and the strength of the magnetic field can be increased until the iron core becomes saturated.
This brings us to the end of the theoretical overview. In the following video, we'll look at the different types of electrical machines and show you what's inside the motors on the table.
Bye!
Bye!